Hey everyone, welcome back, and today let's solve Leetcode problem 2654 titled Minimum Number of Operations to Make All Array Elements Equal to 1. So we're given a zero-indexed array nums consisting of only positive integers, and we can do the following operation on the array any number of times, a keyword being any. We can select an index I such that I is in between and equal to 0 and n minus 1. And the reason why it's n minus 1 is because we're going to be taking the GCD of nums at I and nums at I plus 1 and replacing any one of those two indice values with that GCD value. Right? And we have to return the minimum number of operations to make all the elements of nums equal to 1, but if it is impossible to do so, we then have to return -1. And it kind of just quickly defines the definition of what a GCD is. It's essentially just two integers, or rather, it's essentially just the greatest common divisor among two different integers. We just call that the DCD, or greatest common divisor. So in example 1, we have our input array nums to be 2634, and in this case, the minimum number of operations to make all the elements in this array to be 1 is 4. And the way we do that is first choose index 2, so that would be this value 3. Taking index I plus 1, or 2 plus 1, we'd get index 3. And index 3 is 4. So we're essentially just going to first take the GCD of 3 and 4. That, of course, is simply just 1. Now, we have the choice of replacing either index at I or this 3, or either index at I plus 1 or this 4 to be 1. We would replace this 3 to be 1, and so we'd get 2, 6, 1, 4. Then we choose index 1, so this 6, and replace that to be a 1. So then we'd have 2, 1, 1, 4. And then we do it for index 0, and finally for index 2, and replace this final 4 to also be a 1. So eventually we're going to get all 1s, which kind of leads us to the main observation to make, which I'll get to in a few minutes. Now, applying the same logic to example 2 here, notice how we can't actually do anything with this input array, because every single value in this input array is even. In other words, every single value in this input has a divisor or factor of 2. And since 2 is also in this input array, regardless of which pair of numbers I have, the maximum, or rather the GCD, is always going to be 2, and so I'm always going to be just essentially stuck in a loop of all 2s. I can never make any elements equal to 1. And so that's going to be a -1 output, because it's impossible to make all the integers in this input array to be 1. So for the constraints here, rather small for the length of our input array nums, it's only going to be between 2 and 50, but any value in the input array nums at any index I is going to have a value between 1 and 10 to the 6th power, in other words, 1 million. Which leads us to, again, like I talked about, our main observation. And that is, like we saw in example 1, the GCD of 1 and any other element or any other digit, regardless of what that any other digit is always going to be equal to 1. Because the only factor of 1 is 1. So 1 with any other pair or any other element in its pair always is going to have a GCD of 1. And so what you really have to get from that is, once a single 1 exists in the array, we simply just propagate the 1s outward, turning each non-1 into 1 in one operation each. Sorry about that, kind of a overdose of 1s, right? Now, if there are k1s already and n length, the answer would simply just be n minus k. Why? Because each non-1 element really just needs exactly one operation. And that's if we know that at least one, or rather a single 1 already exists in the array, or we get it from an operation. Like we saw in example 1. We took the GCD of 3 and 4 to be 1. Once we got that single 1 to exist, we simply propagated outwards until all the elements had a value of 1, using the GCD of 1 in every other pair. Now, if there aren't any 1s, we have to first create one. Again, like we saw in example 1, right? And to create a 1, we need to find a subarray with a GCD of 1, or in other words, a pair of elements in the original input array with a GCD of 1. And the minimum number of operations to create a 1 from a subarray from nums at index I to j would simply just be j minus I. Why? Because we can repeatedly merge the adjacent GCDs until one position becomes 1. And so to find the shortest subarray whose GCD is 1, we simply just have to call its length to be j minus I plus 1, and the cost to create a 1 would simply just be the length minus 1 to be equal to j minus I. And after that, we'd simply just still need an n minus 1 operations to actually propagate that 1 to the rest of the values in that subarray. And so the kind of total minimum operations would be minimum operations plus n minus 1. Now, if the GCD of the entire array is greater than 1, like we saw in example 2, where it'd be 2 instead of 1, since 2 is greater than 1, and 2 is the GCD of the whole array, that would be impossible. We'd have to immediately return -1, kind of like leading to the observations that we just made through these examples. That's why it's very important to read through the examples and notice any patterns and kind of make any important observations that you can get from the examples. So, what are the data structures that we're going to be using for these problems? We're going to be using, of course, the input nums. We're going to be having a few counter integers like n, like the number of ones we see in the minimum operations that we keep track of. And we're also going to be using a very nice built-in method or function here in Python called math.gcd. Right? That's another reason why I always say, okay, guys, you should use Python for your programming language for data structure and algorithm problems. It has a lot of very, very important and key built-in methods that really simplify the code and problems. Now, I'm not saying it's the end of the world to code out a custom helper function to find manually the GCD of two inputs, or rather of two input integers, but using the math.gcd built-in method in Python simply just makes it a lot easier and a lot more efficient as well. Right? Now, let's go ahead and get into the actual code here. So, I'm going to do this for best practice, although you don't really need to do this when you're working in the code editor built into Leetcode, as everything is already imported and built into, your editor. But we're actually going to be using, of course, the GCD kind of class, or rather the math class, and we're going to be using the GCD method. And so I'm just going to say for math, import GCD. Now, if you're working in an IDE like VS Code or something, you would actually have to use this when you're implementing your solution, but since we're working at Leetcode editor, we don't need to. I'm just going to do this because it really just is good practice. Now, what I always like to do when working with any integer array or any array input problems in general, I always like to store the length of that input array in a variable n. And so I'm going to do the very same thing for this solution as well. I'm going to store the length of my input array nums, in other words, the number of elements in my input, to simply just be n, right? So I have n elements in my input array num. That's very straightforward. Now, essentially, once I get the length and store it in n, now I have to actually count how many elements are already 1 in the array and simply just store that in a count variable. Now, if any ones already exist, we can already use them to convert the neighbors for very cheap number of operations, right? So I'm going to get ones count and simply just be nums.count, passing in a parameter of 1, simply just counting the number of ones, or the frequency of 1, in this input array nums. Again, another very, very helpful built-in method in Python, and another reason why I really recommend using Python as your primary language for DSA problems. It really just simplifies the kind of coding that you have to do, so you can focus more on the conceptual kind of solution and the different algorithms and data structures that you really need to be using. Now, if there is at least one in the input array originally, then we know that the minimum operations is simply just going to be the number of non-ones, which we can calculate from n minus 1's count. And so if that's the case, we can simply return that immediately. That means if we have at least 1, meaning 1's count is greater than 0, we can immediately simply just return the number of non-ones in our input array. Now, that's because each non-1 can really just be turned into a 1 in a single operation using an adjacent 1, simply just propagating outwards from our original 1, or 1's. And so if 1's count, is greater than 0, great, that makes our solution very straightforward. We simply just return the number of non-1's, which is again calculated by the length of the input array nums minus the number of ones we already have in our input, right? Now, another very important observation that we can make. If the GCD of the entire array is already initially greater than 1, it's impossible to ever get a 1. And we see that in example 2. The GCD of the entire array is actually 2. Since 2 is greater than 1, we immediately have to return -1. Now, why really is that? Well, the reason why it's impossible is because every GCD operation preserves that common GCD divisor. And so if every single element has a common factor that's greater than 1, we're never going to get smaller than 1 because that common factor is always going to take priority, right? So we have to simply just compute the GCD of the whole array in the total GCD, and we're simply just going to initialize that with 0 and kind of fold the GCD across the array. So I'm going to set total GCD equal to 0, and again, we're simply just computing the GCD of the whole array and initializing with 0 to kind of just fold the GCD across the array. Now, once we do that, now I'm actually going to iterate through every input num and build up my total GCD value. So for every element x, I'll just say as my iterator in the input array nums, we're going to update or set equal our total GCD to simply just be the GCD, again, a very helpful built-in method in Python, of the total GCD and our current element x. Effectively, we're simply just iterating through each element or number x in the input array nums and updating this total GCD to be the greatest common divisor of the current value of the total GCD and the current element x. And that's basically just going to loop the total GCD to be the GCD of all the different numbers in the entire input array nums. Now, if that total GCD, again, is already greater than 1, that means there's a divisor that's common amongst all the elements in the input array initially that's greater than 1. It's common to all the elements, and so it'd be impossible to create a 1 for any element. And so if that's the case, we immediately return negative 1. So if the total GCD, oops, I don't know why I keep doing that. If the total GCD is greater than 1, we immediately return negative 1, again, like we saw in example 2. Now, once we're done with that, now this is kind of like the main part of this solution. Now we have to actually search for the shortest subarray that has a GCD of 1. And I'm going to simply just initialize the minimum number of operations, simply just an integer variable that we're going to be keeping track of, to a very large number. We can simply just use n as an upper bound plus 1, but anything large above n plus 1 would really work. I'm just using n plus 1 because you don't really need to use a number anything greater than that. Now, the whole point of this minimum operations variable is that it's simply going to hold the minimum number of operations, like the name suggests, that we need to make a 1 from some subarray, and that would equal j minus I. And so I'm going to initialize minimum operations. After I finish this conditional, I'm going to call it min ops, just so it's a smaller length name or variable name, to be n plus 1, the total number of elements in the input plus an extra 1, right? Now, once I actually get this value, I'm going to start my outer loop, right? And my outer loop is basically just going to iterate that from our starting index I from 0 to n minus 1. And for each starting point, we're simply just going to compute the GCDs of the subarrays that start at that index I. So at that index I as our iterator for every I in the range of n. Again, n simply just being the length of our input or the number of elements, we're going to then initialize g to be 0, so that the GCD of 0 and nums at index I would become nums at index I on the first step, and it would kind of it'd be kind of like a convenient folding technique, right? So for every I in this input array nums, or index rather, I'm going to set g to be equal to 0. And now, once I set g to be equal to 0 in each outer loop iteration, I'm then going to begin my inner loop. And my inner loop is basically where I iterate j from I to n minus 1, or I'm essentially just expanding the subarray from nums at index I to j. And for each expansion, we're simply just updating g to the GCD of the current value g and nums at index j. And if g ever becomes 1, we know we've found a subarray from I to j that has a GCD of 1. And the cost to create 1 from that subarray can be calculated as j minus I, the difference between those two indices, and we simply just update the minimum operations number to break to try the next I, because there's really just no need to expand further for the same starting index I, right? That just doesn't make sense. It'd just be a slower overall runtime complexity on average. So the inner loop is going to be using our index j. So for every j in the range, again, we're expanding here. So from I to n simply just being the end of our input array nums, we're going to update g to be the GCD of either itself, its current value, or nums at index j, the value that we're currently expanding with as our iterator. Now, if this value g, or if this value GCD, which is really what it represents, ever hits 1, we know we can then update our minimum operations to simply just be the minimum of either itself or j minus 1. And once we've done that, we can simply just break out of this loop. We can go on to the next index or starting index I. Now, after the scanning all starts, if the minimum operations is still greater than n, which is kind of like our sentinel, that means we didn't actually find any subarray that has a GCD of 1. However, we already checked the whole array GCD, and that's really just for safety, and so if that's the case, we simply just return negative 1 as kind of like our safety net, if you will, right? And so the way we're going to do that is simply just set equal, okay, well, if the minimum operations is equal, to n plus 1, if that's the case, then we simply just return negative 1 as well. That's like our, after scanning starts. Now, otherwise, if that's not the case, we still would need the minimum operations to create the first 1, and then n minus 1 operations to propagate that 1 to all the other elements. And so we'd have to return the minimum operations plus the value n minus 1. And this is a good example of example 1 here, where we didn't start with a 1 in the input, but we could get 1 from 3 and 4, and then propagate that 1 at index 2 backwards or outwards across the elements 2 and 6 and the element 4. And so we then return minimum operations plus, in parentheses, the value n minus 1. And so if I were to submit this, unless I made any syntax errors here, this should be accepted and this should be a valid solution. So let's go ahead and verify that. All right, let's go ahead and see. probably just a very simple, silly syntax error or logic error here. Let me just go ahead and make sure I don't have something dumb. Okay, I got that. Good. That's fine. And you guys can go ahead and just fast forward this part. This is just me debugging my very weirdly typed out code. But don't worry, guys. I promise I did check this before the video, and it did actually get accepted on Leetcode. I probably just retyped it incorrectly as I was going through the solution. That's completely normal. Yeah, don't think that you have to watch this entire part, because I would not. Find the range n, j is 0, g is 0, they in the range I to n, j is 1. Yep. Okay, so I don't exactly see where this main core issue really is. I doubt this is going to help anything. Let's go ahead and see where else I could have made a faulty error. And I also feel free to just fast forward this part if you guys are still watching. And I also will paste in my accepted solution in the description of this video, because this is a little frustrating to say in the least. Okay, yeah, so there is where no, never mind. That's completely fine. In the range of I to n. Yes, I don't exactly see where this error is really sprouting. I'm going to have to go and verify what the issue really is in this solution after the video. I could try spacing things out, but I doubt that's going to make a difference. Total GCD and x. If the total GCD is greater than 1, we do return -1. That's completely fine. Minimum operations is equal to n plus 1. That's correct. Iterate through for I in the range of n. We initialize g to be 0, and for j in the range of I to n, we get the GCD of g and nums at index j. So we're at g. If g is ever equal to 1, though, we simply just set our minimum operations to be the minimum of itself and j minus... Okay, yeah, so there's the issue, guys. This shouldn't be j minus 1. This should be j minus I, the starting index and the current expanded index. That is the main issue that I made. Now, if I were to submit this should be accepted, and this should be a valid solution. So let's go ahead and verify that. And as you can see, this really is just about as efficient as you can get it to be. So sorry for that kind of 1 minute weird pause in the video, but that is the accepted solution, and as you can see, it is really just about as efficient as you can get it to be. So let's talk about how this code works as a whole and how we really solve this problem, kind of in a summary. Effectively, we're simply just first checking, are there any ones already in the input? If there are, well, we know each non-1 element would require exactly one operation to use, and using exactly one adjacent one, and so the answer would simply just be n minus the number of non-ones, or n minus 1's count. Now, if no ones initially exist in our input, then we have to actually check if the GCD of the entire array is greater than 1. If it is, like we saw in example 2, that means it's impossible to actually make all the elements equal to 1, and so we have to return -1, and the reason why is because GCD operations can never introduce prime factors that weren't already possible. Now, if the whole array GCD is 1, we simply just find the shortest subarray whose GCD is 1, and creating a 1 from that subarray would cost j minus I operations, not j minus 1. That's the typing error that I made. Now, after creating that single 1, we'd simply just take n minus 1 more operations to turn the rest into 1s, and so the total kind of answer would be minimum operations plus n minus 1. And another kind of intuition that you guys would take, one observation that we can really make is that once there's a single 1, everything else simply just collapses into 1 in linear time. And so that really main kind of real challenge of this problem is just, okay, we have to build that first one if it doesn't already exist. We have to find that shortest subarray that costs the least amount of operations that has a GCD of 1. That's really what we're doing in the core part of this solution from lines 15 through 21. Now, once we have that covered, let's go ahead and move into the final part of this solution, which is the complexities. So for our runtime complexity, we know the worst case would be the double loop, because for each index I, we'd expand j until probably n, and that would make the algorithm big O of n squared GCD operations in the worst case. Now, we also technically know that each GCD operation on numbers up to m would cost log m time in the usual kind of Euclidean runtime model. And so technically, it would be an overall big O of n squared times the log of m, where m is simply the maximum number magnitude and n is the length of our input. But, more concretely for typical constraints and for the constraints that we saw in the input constraints for this problem, we don't really care about the log m. That's not really going to affect our runtime complexity. That's really just a simple constant. And so really, it's just big O of n squared with the GCD cost suppressed for this video, right? And for our memory or space complexity, That's going to be big O of 1 or constant extra space because we're only actually using a few integer variables. If you go ahead and look at our solution again, we're not actually using any auxiliary memory, no extra data structures that scale linearly with our input. And so this is actually a constant time or big O of 1 auxiliary space or memory complexity, right? So big O of n squared for our runtime and big O of 1 for our memory. So if you guys enjoyed the solution of doing something new, please consider liking this video and subscribing to my channel. And without further ado, I'll see you guys in the next video. Bye-bye.